In the universe, almost nothing dies completely. Massive stars are the best example. They burn through their fuel, collapse, explode, and yet they leave remnants that continue to influence everything around them. Among these remnants, there is one that defies all intuition, a small, dense sphere that concentrates more energy than seems reasonable. It's not a black hole. It's something that still stands on matter. It's a neutron star. And, in a few exceptional cases, it's something even more extreme, a magnetar. To get there, we need to go back to the life of the original star. We're talking about stars with masses at least 10 times that of the Sun. For millions of years, they fuse hydrogen into helium, then helium into heavier elements. Each stage holds the star against its own gravity. There comes a time when the core fills with iron. Iron does not release energy when it fuses. It's the end of the road. Gravity wins. In seconds, the core collapses. The outer layers bounce off that collapsed core. A supernova is born. A fraction of the mass is ejected into space. The rest, the heart of the star, is compressed into an object just about 20 kilometers in diameter. That collapsed core is a neutron star. It contains a mass comparable to that of the Sun in a sphere the size of a city. The density is so high that a teaspoon of this material would weigh hundreds of millions of tons. The gravity on the surface is enormous, but it doesn't swallow everything like a black hole. There is still a solid surface, a crust, a place where magnetic fields anchor. Most of these neutron stars end up with a very strong magnetic field, but still within what we consider normal for these objects. Some manifest as pulsars, emitting very regular radio pulses, rotating several times per second. Magnetars are something else. They are neutron stars in which the magnetic field has shot up to values that don't fit with everyday experience. We're talking about fields up to 10,000 trillion times the Earth's magnetic field. In technical units, on the order of 10 to the 14th power to 10 to the 15th power Gauss, compared to the 10 to the 12th power Gauss of a typical neutron star. That difference is not a simple numerical detail. It changes how matter, light, and even the quantum vacuum around the object behave. Theory suggests that to generate such a field, two factors come into play. On the one hand, the compression of the star's original magnetic field during collapse. On the other, a type of internal dynamo driven by the very fast initial rotation of the newly formed core with hundreds of rotations per second. When those conditions align, the result is a magnetar. When a magnetar is born, it's not only magnetic, it's extreme in every way. Its surface reaches temperatures close to 1 billion degrees for a brief time. At those temperatures, thermal photons have energies comparable to the rest mass of an electron. Particle-antiparticle pairs appear and disappear without pause. The boundary between matter and radiation becomes unclear. At the same time, the object spins at speeds that approach the limit of what physics allows without it disintegrating. The equator moves at significant fractions of the speed of light. If it rotated much faster, the centrifugal force would tear material off the surface. All of this adds up to the crushing gravity and nuclear density inside. In just a few cubic kilometers, limits of temperature, gravity, magnetism, and rotation converge that, in other contexts, we only imagine within a black hole where we cannot observe anything. The most puzzling thing is that despite this combination of extremes, the magnetar doesn't collapse immediately. It's stable, or at least stable enough to last thousands of years. Its magnetic field slows its motion like a cosmic brake that turns rotational energy into high-energy radiation. That's why observed magnetars tend to spin slowly, with periods of seconds much more slowly than millisecond pulsars. This deceleration allows us to measure the strength of the field. The faster it slows down, the stronger that invisible field is. That's where the estimates come from, positioning them as the most powerful magnets in the known universe. Here appears a key difference with black holes. A black hole is a horizon. Everything that crosses that limit becomes inaccessible. Its gravitational field is enormous, but it has no solid surface or crust where tension accumulates. A magnetar does. It has a structure, it has layers, it has a rigid crust subjected to brutal stresses, and a magnetic field that twists and pushes from the inside out. It doesn't need to devour matter to remain violent. Its energy is stored in the field and in its rotation. What we see every time we detect an X-ray or gamma-ray burst is a small leak from that internal reservoir. When we put everything together, the picture is clear. A magnetar is the corpse of a star that refuses to go out. It concentrated a solar mass into a sphere 20 kilometers in diameter. It raised its temperature to levels where matter behaves as a nearly pure plasma of particles and radiation. It spun so fast that it grazed the limit of breaking apart. It amplified its magnetic field to values that make any human magnet irrelevant. And after all that, it didn't collapse into a black hole. It stayed there in precarious equilibrium, like a natural laboratory of extreme physics. That equilibrium is only apparent. There is tension built up in the crust. There are currents inside that sustain the field. There is energy seeking a way out. Every small adjustment can release an amount of energy equivalent to that produced by millions of suns in an instant. These are neutrons, protons, electrons, magnetic fields. The same ingredients we know, pushed to a limit where our equations still work, but on the edge. The magnetar tells us something uncomfortable. Our theories describe these conditions, but perhaps only approximately. In the details, in the small discrepancies between calculation and observation, there may be hidden new physics. Let's imagine for a moment that the magnetar disappears and only its magnetic field remains. Nothing else. No crust, no neutrons, no core, just field lines crossing space. On a human scale, that makes no sense. We always associate magnetism with something material, a magnet, a wire with current, an electromagnet in some junk. Around a magnetar, that intuition breaks down. The field is so dominant that matter seems like a secondary detail. What rules is magnetism? The star is almost an excuse to hold it in place. On Earth, we live with weak magnetic fields. The Earth's field guides compasses and helps deflect charged particles from the solar wind. Its intensity is just a few tenths of a Gauss. A refrigerator magnet reaches about 100 Gauss. A medical MRI scanner works with fields up to tens of thousands of Gauss. That already seems huge, to the point where metal objects have to be removed from the room because they literally fly off. In a normal neutron star, the field can reach trillions of Gauss. Impressive. However, a magnetar goes beyond that, several orders of magnitude higher. In a magnetar, the field can exceed 10 to the 14th or 10 to the 15th Gauss. It's a number hard to digest. One way to imagine it is to think in terms of stored energy. A magnetic field stores energy in the space it occupies. the more intense it is, the more energy per cubic centimeter. Around a magnetar, the energy of the field in a volume the size of a room can be comparable to all the energy the sun releases in a year. It's a real physical medium, not just a vector on a chalkboard. It's not a passive property. It's a pressure, a tension, a force distributed throughout space. This magnetic tension competes with everything else. It competes with the thermal pressure pushing outward. It competes with gravity pulling inward. It competes with the rigidity of the crust. The field lines curve, twist, anchor to the star's surface. If they deform, they store energy like a twisted spring. At some point, that spring gives way. The field reconfigures, reconnects, straightens suddenly. The energy that was trapped in that geometry is released in the form of radiation, particles, waves. What, on a human scale, would be a spark, here becomes a flash of X-rays and gamma rays. But before we get to those bursts, it's worth stopping to consider something simpler. What this field does to quiet matter. In a laboratory, a magnetic field influences charged particles. It deflects electrons, pushes ions, makes charges spiral. In a magnetar, this is taken to the extreme. Electrons get trapped in extremely tight orbits, clinging to the field lines. Their movement is quantized and their energy levels are stepped. The freedom to move in any direction is lost. Quantum physics ceases to be a small correction and begins to govern everything. This has direct consequences for atoms. Under normal conditions, an atom has electrons orbiting in a roughly spherical cloud around the nucleus. In a magnetar field, that cloud gets flattened and elongated. The atom turns into something like a needle aligned with the field. The chemical bond no longer resembles what we know. Molecules that would be stable on Earth would break apart. Others, impossible here, might form there. The matter in the magnetar's crust is not only dense, it is subjected to a magnetic order that reconfigures it at its most basic level. Further from the surface, the field continues to impose conditions. A charge attempting to move perpendicular to the field feels a force that curves it. If the energy is low, the field wins. The charge is forced to follow the lines. That's why the environment around a magnetar is filled with particles flowing along the field lines as if traveling invisible tracks. Structures called magnetosphere and magnetotail are formed, similar in concept to those on Earth, but taken to the extreme. There, particles are accelerated to enormous energies. These particles, as they curve, emit radiation. This is how much of the persistent brightness of these objects in X-rays is born. At even greater distances, the field weakens, but it's still intense compared to anything human. If we could bring a common object close, even thousands of kilometers away, the induced currents could disintegrate it. A piece of metal would experience internal forces that would tear it apart. Complex organic molecules would break. Any magnetic information storage device would be erased. There's no need for an event horizon or infinite gravity. The magnetic field alone is enough to redefine what surviving means near one of these stellar corpses. In this context, the neutron star no longer seems like the center of the story. The protagonist is the energy of the field. It is the field that drains rotation, converts mechanical energy into radiation, deforms the crust, accelerates particles, reorganizes matter. The star's interior feeds the field, but what we observe from afar are its effects. Each pulse, each flash, Every variation in the intensity of X-rays is a signature of how that field is changing. It's like reading the activity of an engine without seeing it, only observing the smoke, the vibration, and the noise. The deepest detail is that this field not only dominates matter, it begins to move into a more subtle terrain. It approaches a scale where even the vacuum itself ceases to be neutral. In quantum physics, the vacuum is not a perfect nothing. It's full of fluctuations. Pairs of particles and antiparticles appear and disappear in brief intervals. Most of the time, these fluctuations leave no observable trace. They are like background noise. However, if an electric or magnetic field of sufficient intensity is introduced, that noise responds. The vacuum becomes polarized. It behaves like a medium. A magnetar operates very close to that limit. Its magnetic field reaches and exceeds the critical value beyond which quantum electrodynamics equations predict strange effects. Light passing through it no longer sees space as a transparent, homogeneous stage. It sees a medium that treats it differently depending on its polarization. A photon may change direction, split, or transform. The magnetic field not only orders particles, but also orders the vacuum that separates them. And this forces us to accept an uncomfortable idea. Under certain conditions, the empty space behaves more like an optical crystal than a simple stage. What's fascinating is that to study this regime, we can't just build a bigger magnet on Earth. We can't reach it. The best laboratories barely touch the fields where the vacuum's quantum response begins to emerge. The magnetar is ahead of us by many orders of magnitude. It's the experiment we'll never be able to set up already assembled, silently spinning in some corner of the galaxy. All we can do is observe its light, its bursts, its brightness changes, and try to reconstruct what is happening in that environment where the magnetic field dominates even what we thought was immutable. When the vacuum stops being empty. In classical physics, the vacuum is nothing. It is the stage where the action takes place. What matters are the particles, the fields, the forces. Empty space is transparent, flat, neutral. Light travels through it at a constant speed. It doesn't slow down, it doesn't curve, it doesn't change its nature unless it encounters matter or gravity. This is the intuition we grew up with, and it works well in almost the entire universe, until one gets close to a magnetar. In quantum physics, this idea starts to crack. The vacuum is no longer nothing. It's a state full of fluctuations. Pairs of particles and antiparticles appear and disappear in such short times that we cannot capture them, but we can feel their collective effect. That is what quantum electrodynamics describes, the theory that unites quantum mechanics with electromagnetism. According to this theory, if you subject the vacuum to a very intense electric or magnetic field, those fluctuations respond. The vacuum becomes polarized. It behaves like a physical medium with measurable optical properties. There is a scale that marks the boundary between strong field and extreme field. It's called the Schwinger critical field. It is the value at which the field is so intense that it can efficiently pull electron-positron pairs from the vacuum. In magnetic units, it's on the order of 4 times 10 to the 13th power Gauss. Below that value, the quantum effects in the vacuum are subtle. Above it, they become dominant. Magnetars operate right there, and often beyond. Their fields reach 10 to the 14th or 10 to the 15th Gauss. It's not a mere numerical curiosity. It means that the environment around a magnetar is within the regime where the vacuum stops behaving like a simple transparent stage and starts to act like an exotic material. One of the most direct consequences is called vacuum birefringence. The name sounds technical, but the idea is simple. On Earth, some crystals do something similar. If you look through them, light splits. One beam enters, two come out. Each one has a different polarization and travels at a slightly different speed. That's birefringence. In the vacuum without matter, classical electrodynamics says this shouldn't happen. Light shouldn't notice anything. However, quantum electrodynamics predicts that in the presence of an extreme magnetic field, the vacuum becomes birefringent. Light with different polarizations experiences a different refractive index. It travels as if space were an invisible crystal. Magnetars are natural candidates to observe this effect. They emit polarized X-rays from their hot surface and from the magnetosphere. That light must pass through an environment dominated by the magnetic field. If the vacuum is birefringent, the polarization should emerge very ordered. That's exactly what the new observations with X-ray polarimetry satellites are beginning to show. Missions like IXPE have measured very high degrees of polarization in magnetars, in some cases over 40 or 50%, with variations depending on the energy and the phase of rotation that match what the models, including vacuum birefringence, predict. It's not yet a unique proof, but it's growing evidence that around these objects the vacuum behaves like a real optical medium. Birefringence is not the only quantum effect of the vacuum in play. There are more radical processes. One of them is photon splitting. Under ordinary conditions, a photon doesn't split into two just because. It needs to interact with matter or other fields to redistribute its energy. In an extreme magnetic field, the situation changes. Quantum electrodynamics allows a high-energy photon to turn into two lower-energy photons, even in the absence of matter. The field acts as a catalyst. It's a non-linear process. It doesn't occur at low intensities, but in the environment of a magnetar, it can become relevant. Theory shows that above the critical field, the probability of photon splitting increases and can compete with other processes, such as pair creation. If you look at a magnetar's radiation spectrum with this idea in mind, you gain a new tool. Very high-energy gamma radiation can transform into a cascade of less energetic photons before escaping. This softens the spectrum, attenuates the hardest part, and redistributes the energy. Instead of imagining that the light we measure came out intact from the surface or the magnetosphere, we must accept that it passed through an active quantum filter. This filter depends on the field's intensity, the geometry of the magnetic lines, and the angle at which the radiation propagates. It's not a simple technical detail. It affects how we infer the properties of the object from the light we receive. Added to this is the polarization. The combination of birefringence and photon splitting causes the modes of light to mix, separate, and recombine. A beam initially with little polarization can exit much more ordered after passing through the region near the magnetar. The direction of the field selects preferred modes. That's why polarimetry is so valuable. It doesn't just tell us how strong the emission is. It gives us information about the structure of the magnetic field and the presence of quantum effects in the vacuum. Each variation in the polarization angle along the magnetar's rotation provides a clue about how the field lines are oriented in space. These phenomena make magnetars unique laboratories to test quantum electrodynamics in a regime inaccessible on Earth. Experiments like PVLAS try to detect vacuum birefringence using intense lasers and strong magnetic fields in laboratories. But even then, the fields achieved are millions of times weaker than those of a magnetar. What is a tiny correction in a lab becomes a dominant effect around these objects. That's why there is so much interest in combining observations of polarized X-rays, theoretical models, and numerical simulations. Every observed magnetar adds a point on the map of how the quantum vacuum behaves under extreme stress. The vacuum near a magnetar is not a passive backdrop. It's a medium that can split high-energy photons, alter the propagation speed of light based on its polarization, and amplify the coherence of radiation. The boundary between matter, field, and space becomes blurred. Light no longer travels through a neutral stage. It travels through an environment that selects, filters, and reorganizes it. The impossible crust and stellar earthquakes. The surface of a magnetar is unlike anything we can step on. It's not rock, ice, or metal in the everyday sense. It's frozen nuclear matter in a solid structure, crushed by immense gravity and pierced by a magnetic field that constantly tries to deform it. This layer is called the crust. It's only a few kilometers thick, maybe less, over an object with a radius of 20 kilometers. But its behavior is responsible for some of the most violent phenomena we have seen in high-energy astrophysics. The crust is essentially made up of tightly packed heavy nuclei, surrounded by a sea of degenerate electrons. Further down, towards the interior, the density rises so much that the nuclei begin to deform and form exotic structures. This region is informally known as nuclear pasta, layers, tubes, strange shapes that minimize the energy of the system under brutal pressure. Everything is compressed beyond any terrestrial solid. 1 cubic centimeter of this crust would weigh more than a mountain. On this already extreme structure rests the magnetar's magnetic field. The field lines are not decorative. They anchor in the crust, entering and exiting the surface. If the fluid interior of the neutron star changes, the field tries to readjust. If the rotation slows down, the lines may twist. Each of these deformations transmits tension to the crust, as if someone were twisting a metal bar from the inside. While the crust holds, elastic energy accumulates. When it gives way, that energy is released in an instant. That giving way is not a metaphor. We're literally talking about fractures, slips, creaks in a solid surface under impossible conditions. These episodes are called starquakes. The term is not poetic, it's descriptive. Just like an earthquake on Earth, there's an accumulation of tensions followed by a sudden release. The difference is in the scale. The energy released in one of these events can exceed the total energy of the earthquakes recorded by humanity in a year, concentrated in a fraction of a second. When a portion of the crust breaks, it's not just the surface that vibrates. The magnetic field anchored in that region also reconfigures. It's like releasing a rubber band that was stretched to its maximum. The field lines can reconnect, change topology, and send Alfvén waves into the magnetosphere. These waves drag charged particles, accelerate them, and trigger a kind of global spark. Suddenly, the region around the magnetar is filled with very hot plasma and high-energy radiation. From afar, all this looks like an X-ray and gamma-ray burst. In some cases, it starts with a brief, saturated flash, followed by a tail that vibrates in sync with the magnetar's rotation. This is the signature that the event occurred on the surface of a rotating compact object. The quasi-periodic oscillations detected in some large flares seem to be linked to the vibration modes of the crust itself. It's like hearing the sound of the magnetar through its high-energy light. The pressure the crust bears is so immense that it's natural to wonder how it doesn't collapse entirely. The answer lies in the balance between forces. Gravity pushes inward, the degeneracy pressure of electrons and neutrons pushes outward, the magnetic field introduces lateral and vertical stresses. As long as that balance holds, the neutron star remains stable. But locally, in patches of the crust, the balance can break. These patches are where starquakes are born. Not all starquakes produce the same spectacle. Some manifest as short, relatively modest bursts, small changes in X-ray flux. Others trigger giant flares. These giant flares are rare events but unforgettable. In them, the energy released in less than a second can equal the energy emitted by the sun in tens of thousands of years. The initial flash can saturate detectors, reflect in Earth's ionosphere, and interfere with radio transmissions. And all of this originates from a layer of matter only a few kilometers thick that fractured. These phenomena also alter the magnetar's rotation. When the crust breaks, the mass distribution changes slightly. The result can be a small jump in the spin period, a glitch. In the timing records of X-ray pulses, these changes appear as sudden adjustments. It's another way to trace the internal mechanics of the object. The idea that an earthquake in a body of 20 kilometers can be measured from thousands of light years away may seem exaggerated, but that's exactly what we are doing. The crust doesn't just store magnetic tension, it also channels currents. When it fractures, it can modify preferred paths for the flow of electricity within the star and its magnetosphere. This change in the currents alters the field pattern. Imagine a dynamo that suddenly changes its internal configuration. The field may intensify in some places, weaken in others, open new lines that connect regions that were previously isolated. Each of these reconfigurations helps explain why magnetar activity often comes in storms, swarms of bursts, followed by periods of relative calm. It's worth emphasizing something. On a microscopic level, there are no mysterious ingredients. They are protons, neutrons, electrons interacting through forces we know. What makes the crust extraordinary is the combination of density, magnetism, and gravity. It's a regime where many of our intuitions become useless. Concepts like elasticity or rigidity are redefined. What we would call a tiny deformation on Earth, there releases enough energy to fry the electronics of a distant satellite. For theorists, these stellar earthquakes are a tool. From the energies released, the duration of the bursts, and the subsequent oscillations, they can infer properties of the crust. How thick it is, how rigid, how it couples with the fluid interior. They can also test different composition models, see if it's better to imagine a crust rich in certain elements or others, and whether the nuclear pasta has enough rigidity to transmit the vibrations we observe. Each recorded flare adds another piece to that reconstruction. The bursts that touch Earth. The story of a magnetar burst doesn't end with the fractured crust. It keeps traveling. What happens in that solid layer translates into light waves and particles shot out at the speed of light. Most of the energy travels in the form of X-rays and gamma rays. It's highly energetic radiation, much more than visible light, much more than ultraviolet rays that concern us with the ozone hole. This radiation doesn't stop unless it encounters matter. Between the magnetar and us, for most of the journey, there's just nearly empty space. When a magnetar produces a giant flare, the initial flash is very brief. It lasts tenths of a second. That pulse concentrates much of the total energy. Then a longer tail may follow, modulated by the object's rotation. If the magnetar is in our galaxy or a neighboring one, high-energy detectors record it as a sudden spike in counts, sometimes so intense that they saturate the instruments. The magnetar doesn't have to be close. At tens of thousands of light years away, the flash is still measurable. The first big alert of what a magnetar could do came on March 5, 1979. Several military and scientific satellites detected an unexpected gamma-ray pulse. It came from the direction of the Large Magellanic Cloud. The burst was so intense that for a moment it outshone all other gamma-ray sources in the sky. It wasn't until years later that it was understood that the probable origin was a magnetized neutron star, what we now call a magnetar. It was the first recorded giant flare. Another key episode came on December 27, 2004. On that day, a magnetar named SGR 1806-20, located about 50,000 light-years away, produced such a powerful flare that, for a fraction of a second, its gamma-ray brightness exceeded that of the entire Milky Way. Several NASA satellites and others from different agencies saturated their detectors. The radiation wave struck Earth's magnetosphere and upper atmosphere. It didn't cause direct damage to the surface, but left measurable traces in the ionosphere and in some very low-frequency radio communications. That's where the story connects with us. Earth's atmosphere is an effective defense against high-energy radiation. X-rays and gamma rays are absorbed in the upper layers tens or hundreds of kilometers above the ground. This means they don't reach the surface in significant amounts, but that absorption is not harmless. It ionizes molecules, temporarily alters air conductivity, and changes how radio waves propagate that bounce off the ionosphere. From a physics point of view, a magnetar flare is a sort of unexpected experiment on our atmosphere. When one of these radiation waves reaches Earth, X-ray and gamma-ray observatories aren't alone in noticing it. Networks of antennas that monitor very low-frequency radio wave propagation also detect changes. Suddenly, the ionospheric region that reflects those waves becomes more ionized. It sinks or rises. The signals are either attenuated or enhanced. By comparing the time and intensity of these anomalies with satellite records, researchers can reconstruct how the high-energy pulse interacted with the atmosphere. These effects have raised an inevitable question. What would happen if such a flare occurred much closer? The examples we have are tens of thousands of light-years away. At that distance, the radiation is intense for the instruments, but moderate for the biosphere. If a magnetar produced a giant flare just a few light-years away, and the radiation beam pointed directly at us, the consequences could be severe. Theoretical models suggest that there could be a significant disruption of the ozone layer, a temporary increase in ultraviolet radiation flux at the surface, and effects on the biological chain. It's an extreme scenario, and we don't know of any dangerous magnetar so close, but it illustrates the power of these bursts. Beyond speculation, the fact is that today we use these events as tools. Every time a magnetar lights up, we gather data about the structure of its magnetic field, its crust, and how high energy radiation propagates through interstellar space. We also test our technological infrastructure. Satellites, detectors, communication systems, everything is subjected to a radiation peak that effectively serves as a stress test. So far, the observed impacts have been small, but they were enough to remind us that we live under an active sky. There is another level at which these bursts touch the Earth, the level of time. Each photon we detect from a giant flare left the magnetar's environment thousands, sometimes hundreds of thousands of years ago. What we see today is the echo of a fracture that occurred when Earth had a different history, other climates, and very different life forms. The signal takes so long to arrive that by the time we receive it, the magnetar has probably already changed. Maybe its field weakened, maybe its crust stabilized, maybe it's no longer an active magnetar. Looking at its bursts is like looking at an archive of processes that happened in a distant past. To better understand them, astronomers compare giant flares, intermediate flares, and more modest bursts. They analyze durations, energies, pulse shapes, and oscillating tails. They search for logic behind the apparent unpredictability. The question is simple: is there a pattern? Is there a cycle? Can we anticipate when a magnetar will produce a big event? So far, the answer is no. Storms of bursts have been detected, active periods followed by long silences, but there's no clear schedule. This makes every detection a surprise. This unpredictability becomes even more intriguing when we extend the frequency range. Not all the energy from a magnetar is emitted in X-rays or gamma rays. Sometimes what we see are bursts in radio waves, extremely brief signals, milliseconds long, with an enormous amount of energy compressed into that flicker. Some of them come from our galaxy and can be associated with known magnetars. Others come from far away, from other galaxies, and are so intense that, for a moment, they rival the energy radiated by entire stars. These signals have a specific name: fast radio bursts, FRBs. They are one of the youngest enigmas in modern astrophysics. Discovered just over a decade ago, they have forced a revision of the entire catalogue of possible compact sources. Among those sources, magnetars occupy a privileged place. The flares that hit our atmosphere and modify the ionosphere are just one side of the story. The other is in those radio bursts that seem to come from compact objects that, in many cases, behave like magnetars in an extreme mode. The mystery of the radio bursts. At first, fast radio bursts seemed like an instrument error. Brief pulses lasting milliseconds that appeared once in a spot in the sky and never returned. When the data was carefully reviewed, they were still there. They were real, they were intense, and they were strange. If you want to compress so much energy in such a short time, the source has to be very small. It can't be an entire galaxy, nor a giant star. Only something compact, the size of a city or smaller, can turn on and off that quickly. This pointed to neutron stars or black holes, but doing what? Nobody knew. For years, most of these bursts were one-offs, a single pulse detected once with no repetition. This made things complicated. If the source exploded and vanished, it could have been a catastrophic event, like the merger of two neutron stars or the final collapse of a massive star. But then the rebels appeared. Some spots in the sky started to pulse more than once. They weren't very frequent, but they repeated, sometimes days later, sometimes months. It was enough to rule out scenarios that would destroy the source. Whatever it was, it survived to emit again. These bursts were named fast radio bursts, or FRBs, and those that repeated were called repeaters. They were a gift for astronomers. A unique FRB is a burst that came, was recorded, and then left. There's no second chance. Instead, a repeater allows something crucial: organizing observation campaigns. Several radio telescopes can point to the same spot, wait, accumulate hours of silence until the next pulse finally comes. It's this repetition that allows us to dissect the signal, measure how the frequency changes during the pulse, how the intensity varies, and how the radio is polarized. Each new burst adds a layer of detail. The next step was to figure out where they were coming from. By measuring how dispersed the signal arrives, we can estimate how much matter it passed through on its journey. This dispersion acts as a distance indicator. The first calculations showed something surprising. Many FRBs seem to come from cosmological distances, billions of light years away. This implies enormous energies at the source. It means that what lasts milliseconds in our detectors could have released in that brief moment as much energy as the sun does in days. If these energies come from an object the size of a city, the conclusion is inevitable. We're dealing with extreme physics. For a long time, it was all indirect evidence. We knew the source was compact. We knew it wasn't destroyed when emitting. We knew it repeated in some cases. What was missing was a direct connection to a specific object. That connection came when several radio telescopes detected a millisecond radio burst from a magnetar in our own galaxy, while X-ray and gamma satellites recorded a flare from the same location. The link was clear. For the first time, an FRB was unmistakably associated with a magnetar. This doesn't mean that all FRBs come from magnetars, but at least some do. And it gives us a plausible mechanism. We know that magnetars produce high-energy flares when their magnetic field reconnects or when their crust fractures. We know that these flares accelerate charged particles in their magnetosphere. The challenge is to generate radio waves, a much lower frequency radiation than X-rays and gamma rays. It's not enough for particles to emit. They have to do so coherently, like a laser, to reach the observed brightness. The theory that currently dominates the debate proposes something like this. In an external region of the magnetar, highly twisted magnetic field lines break and reconnect. This reconfiguration creates very strong transient electric fields. These fields accelerate electrons to relativistic speeds. The electrons, moving within the intense magnetic field, emit synchrotron radiation. Under normal conditions, this radiation would be weak. But if the plasma organizes in a certain way, the electrons can emit in phase coherently. The radiation is then brutally amplified and emitted in a narrow beam of radio waves. If that beam crosses Earth, we see an FRB. If it points elsewhere, the event goes unnoticed. Repeaters add complexity. Some, like the famous FRB 121102, emit bursts in clusters, hyperactive days with dozens of pulses, followed by weeks or months of silence. When these cycles are analyzed statistically, structure emerges. Activity periods that repeat have been identified. This doesn't mean that every cycle produces bursts, but there are preferred windows in which the source is more talkative. This points to external modulation. Something, perhaps a binary orbit or the precession of the magnetar's axis, opens and closes the window in which the beam reaches us. One possible scenario is a magnetar in a binary system. A massive star orbits around it. Every time the magnetar gets closer to its companion, tides stretch its crust and strain its field. Stress accumulates and is released in the form of starquakes and flares. Some of these flares produce coherent radio if the axis of the beam tilts enough. That radio reaches Earth. The result is a pattern, periods of higher burst probability around a certain point in the orbit, and silence the rest of the time. But even within the active window, the emission is capricious. Not all orbits guarantee a visible burst. What's interesting is that different repeaters show different cycles. One may have a period of just a few dozen days, while another could last several months. This suggests that not all architectures are the same. There could be magnetars in close orbits, others in wide orbits, some precessing on their own without a companion. The fine detail of these cycles speaks to masses, distances, and geometries we're still trying to reconstruct. Models invoke small orbiting bodies, debris disks, even precession induced by internal deformations of the magnetar. There's still no consensus, and, as always in science, there are skeptical voices. Not all repeaters fit well into the magnetar mold. Some are too energetic. Others show pulse durations or structures that are difficult to reconcile with current models. This opens the door to the possibility of multiple populations. Perhaps some FRBs are produced by young magnetars in galaxies with intense star formation. Others could arise from mergers that don't completely destroy the neutron stars. Some, more exotic, have been associated with ideas like strange matter or topological phenomena in space-time itself. For now, magnetars are the most sober and well-supported explanation for a significant fraction of FRBs, but they are likely not the only protagonists. Meanwhile, even without knowing exactly how each pulse is produced, we already use FRBs as tools. The radio signal travels through the universe, passing through ionized gas between galaxies. That gas disperses the signal, delaying lower frequencies more than higher ones. By measuring how much the pulse stretches in frequency, we can estimate how many free electrons it has passed through. It's a way of weighing the normal matter that resides in intergalactic space, matter that we cannot see with optical telescopes. FRBs have thus become probes of the cosmos's structure. They are also an indirect census of compact objects. If many FRBs come from magnetars, and we detect thousands of FRBs from all directions and cosmic eras, the conclusion is that magnetars must be very common. We don't see most of them directly. We only detect the sources that, by geometric chance, point their beams toward us at the right moment. It's like trying to estimate how many lighthouses there are on a planet by only seeing the flashes that, at some point, align with our telescope. What we see is the tip of a massive iceberg. The hidden world, what we don't see in the galaxy. In the sky, we don't see everything that's there. We see what emits, what points toward us, what overcomes the background noise of our instruments. The same happens with magnetars. We know a handful in the Milky Way and in nearby galaxies, but everything suggests they are only a small fraction of those that really exist. Most remain silent, turned off, or hidden behind clouds of gas and dust that block their light. To begin with, there is a basic bias. We discover magnetars because they do something striking. They produce X-ray or gamma-ray flares. They pulse in X-rays slowly and persistently. In some cases, they emit radio bursts. If an object doesn't do any of that while we observe it, it is invisible to us. It might be there, slowly rotating, with a still strong magnetic field, but without episodes of stress. In catalogs, it does not appear as a magnetar. At best, it shows up as a weak X-ray source, or not even that. Additionally, magnetars are young on a cosmic scale. They are born from the collapse of massive stars that lived only a few million years. After the supernova, they spend a few thousand years in an extreme mode, with enormous magnetic fields and intense activity. Then the field weakens. The magnetic break and energy loss gradually dim the brightness. As they cool, their thermal emission shifts to energies that are no longer easy to detect. The magnetar phase doesn't last forever. It is a stage, not a permanent condition. If you combine both ideas, the first rough estimate appears. We only see magnetars that are in the active phase, and within those, only the ones currently emitting in a detectable range that we are monitoring. It's a double selection. It's like trying to know how many volcanoes there are on Earth by only looking at eruptions that happen during a stormy, foggy night. What you see is real, but it is heavily cut off. Astronomers are trying to go beyond this partial view. One way is through supernova rates. We know how many massive stars explode on average per century in our galaxy. We also know how many pulsars and magnetars we have detected. If only a fraction of supernovas give rise to magnetars, and if the active life is short, it makes sense that we see so few. By adjusting those numbers, typical estimates suggest that the Milky Way could harbor tens of millions of neutron stars in total, of which a significant fraction would have gone through a magnetar phase at some point. Another clue comes from FRBs and giant flares. If we associate at least part of those phenomena with magnetars, we can count how many events occur per unit of volume in the universe. Then, comparing it with the rate of massive star formation, we can infer how many young magnetars must exist to generate that statistic. The exercise has many uncertainties, but the recurring conclusion is that we are not dealing with rare oddities. There should be young magnetars in much of the galaxies with strong star formation. However, the Milky Way is a complicated place to conduct censuses. We live inside a disk full of dust, gas, and all kinds of sources. There are regions where soft X-ray absorption is enormous. There, a magnetar might ignite, and we would barely see a dampened part of its harder emission. If the flare is not intense enough, it will go unnoticed. If it occurs in a part of the sky where no satellite is looking at that moment, it will be completely missed. Our vision has gaps, both in time and direction. We are also limited by the sensitivity and resolution of the instruments. The first generations of X-ray telescopes could only detect the brightest sources. Today, with more modern missions, we find weaker, more distant and more complex objects. Each new tool adds more candidates. The same happens in radio. Next-generation radio telescopes, with wider fields of view and greater data processing capacity, are revealing a growing population of transient sources. Among them, there are likely magnetars that previously escaped our detection. All of this leads to a key idea. The population of magnetars is not static, it is dynamic. At any given moment, some are being born, others are active, and some are shutting down. Viewed together, they form a kind of conveyor belt of objects that enter and exit the magnetar phase. During the first few thousand years, an individual may produce multiple episodes of activity, bursts, flares, changes in its spin rate. Later on, its field reorganizes, weakens, and relaxes. To our instruments, it goes from being a magnetar to being an ordinary neutron star, or even an almost invisible object. From the galaxy's point of view, that legion of compact corpses is important. Each young magnetar injects energy into the interstellar medium. Its flares heat the gas, ionize regions, and perhaps contribute to maintaining a faint layer of plasma in certain areas. Its progenitor, supernovae, scatter heavy elements, enriching the clouds from which new generations of stars and planets will form. Though we only see a few, the cumulative effect of all the magnetars that have existed and will exist is part of the energy breathing of the Milky Way. There is another dimension in which these silent objects influence: gravity. Every neutron star is a compact mass that orbited, and perhaps still orbits, around the galactic center. Some are in binary systems, while others were ejected by asymmetric kicks during the supernova and traverse the halo at speeds of hundreds of kilometers per second. They carry with them their magnetic field, their activity history, and their potential to reactivate in isolated episodes. A mature galaxy like ours is, in part, a graveyard of moving compact stars. All of this makes attempting to map the magnetars a fascinating challenge. It's not enough to list the ones we know, we must infer the ones we don't see. To do this, population models are used. Simulations are run for massive star births, their evolutions, their explosions, and the probability is assigned that the remnant will be a magnetar. Then, the life of these objects, their trajectories and their active phases are followed. The result is a sort of synthetic galaxy that can be compared with real observations. By adjusting parameters, the goal is to close the gap between what is observed and what is expected. The results are clear in one aspect: what we see is only the surface. For every identified magnetar, there should be many more that have never been classified as such. Some were active when no one was looking, others shut down too quickly. Some are hidden in directions poorly covered by our instruments. It's not a cosmic conspiracy, it's simply the consequence of having limited instruments in an enormous universe. From the human side, this changes how we think about these objects. They stop being rare oddities and become a natural part of the life cycle of massive stars. Almost all galaxies with star-forming regions should routinely produce magnetars. Some of these magnetars will live quiet lives. Others will be sources of FRBs. Others will produce giant flares. None of them carry a sign identifying them in advance. We only know how they behave when they are already in action. And here comes the link to the rest of the universe. If our galaxy, which is not particularly extreme, harbors a hidden population of magnetars, what happens in more active galaxies? When a magnetar disguises itself as something else. When you look at the catalogue of extreme phenomena in the universe, magnetars almost never appear at the forefront. We see gamma-ray bursts, superluminous supernovas, rare transients that light up and fade without fitting into any classic category. In many of these cases, the central engine has no face. We only see the end result: hot gas expanding, relativistic jets, light going up and down following smooth curves. This is where magnetars start to appear as silent suspects. Let's take short gamma-ray bursts. These are high-energy flashes that last less than 2 seconds. In that brief moment, they emit as much energy as the sun does in its entire life. For years, it was thought that all these bursts came from neutron star mergers or from neutron stars with black holes. In many cases, this explanation still fits. But when looking more closely at some light curves, anomalies appear. After the initial burst, some events show a plateau, a nearly constant brightness for minutes or hours before it fades. It's as if someone is still feeding the explosion from within. This plateau is hard to explain if the collapse only leaves behind an inert black hole. However, it makes sense if the result of the merger is, at least temporarily, a very massive and very fast magnetar. That newly born object spins hundreds of times per second. Its magnetic field is colossal. As the field slows down the rotational energy is released and injected into the expelled plasma. This injection sustains the brightness of the explosion for a while. Then, when the magnetar loses enough energy or eventually collapses into a black hole, the light begins to fade. Something similar happens with some extraordinarily bright supernovas, the so-called superluminous supernovas. In these, the amount of light emitted far exceeds that of a typical supernova. The radioactive decay of the nickel produced in the explosion is not enough to explain such energy. An extra source is needed. One option is the interaction with a dense shell of material around the star. Another, increasingly explored, is a young magnetar acting as the central engine. In this scenario, the massive star explodes in a usual way. The core collapses, forming a neutron star, but the initial conditions give rise to an extreme magnetic field. A magnetar is born. During the first days and weeks, this object rapidly loses rotational energy. The energy is deposited into the material expelled by the supernova, heating it from within, making it shine brighter and for longer. The result is a wide, very luminous light curve that does not require impossible amounts of radioactive nickel. These ideas are not pure speculation. When superluminous supernova models are adjusted to observations, the parameters representing a magnetar take reasonable values for a young, extreme neutron star. There is no need to violate any known laws. It's enough to accept that nature, in some cases, pushes the combination of rotation and magnetism to the limit. The magnetar becomes a sort of internal battery that feeds the explosion far beyond the initial burst. At other times, the magnetar might be the consequence, not the cause, of a larger event. Imagine the merger of two neutron stars. The final result could be a black hole, but between the merger and that final collapse, there could be an intermediate phase, a hypermassive object, temporarily held up by its rotation and internal pressure. During this period, the core could behave like an extreme magnetar. Its field organizes the plasma, launches jets, and feeds electromagnetic emission. When rotation can no longer sustain that structure, the object collapses and the engine shuts down. Seen from afar, all of this blends together. A merger that forms a short-lived magnetar can be seen as a short gamma-ray burst with a plateau. A supernova with a central magnetar can appear as a superluminous supernova. And, in both cases, if the jet points in a different direction, or if the environment absorbs part of the signal, the result can be a high-energy transient that doesn't fit into any simple box. A catalogued object with a long technical name, registered, classified, archived, but whose real heart is a disguised magnetar. This disguise is not limited to the most spectacular explosions. There are also more modest transients, intermediate duration X-ray bursts that could be due to magnetars in particular environments, for example, in massive star clusters or in very dense gas regions. There, the interaction between the magnetized wind of the magnetar and its surrounding medium can produce structures resembling pulsar wind nebulae, but with different characteristics, more complex light curves, spectra with additional components. Signals that, without a detailed model, just seem strange. For astronomers, this scenario has an important consequence. It's not enough to explain each extreme phenomenon separately. We have to think in terms of central engines. We must ask, in each case, what compact object could be behind the emission? Magnetars, black holes, ordinary neutron stars. Each engine leaves a subtle signature in the shape of the light curve, in the spectrum, in how the brightness changes over time. Among these engines, magnetars have an advantage or a complication depending on how you look at it. They can store and release magnetic and rotational energy over extended periods. To complicate things further, the same type of engine can produce different phenomena depending on the environment. A magnetar in a young, gas-rich galaxy surrounded by dense remnants of its own supernova will not behave the same as one isolated in the galactic halo. The first might generate superluminous supernovas or repeated high-energy bursts. The second may only have a brief active phase and then spend centuries as a relatively quiet neutron star with occasional bursts. In both cases, the central object is a magnetar. What changes is the setting. There is something almost ironic in all of this. To detect a pure magnetar, the ideal situation would be to see it isolated, emitting only its X-ray and gamma light without interference. But many of the most interesting magnetars are submerged in chaotic environments. They are central engines of larger explosions. They're hidden inside expanding gas shells or in distant galaxies where we can barely resolve the affected region. All we receive is the light processed by that entire environment. Despite these difficulties, the picture is becoming clearer. Every time a superluminous supernova fits better with a magnetar-powered model than with other explanations, we gain confidence in the idea that these objects are working behind the scenes. Every time a short gamma-ray burst shows a plateau compatible with a magnetized neutron star engine, we reinforce the connection. Over time, the question stops being, are magnetars real central engines, and becomes, in what proportion do they contribute compared to other engines? In the end, the magnetar appears as a versatile actor. Sometimes it shows itself directly as a pulsed X-ray source with occasional bursts. Sometimes it manifests through FRBs, sometimes disguised as an overly bright supernova or a gamma burst with a prolonged tail. In almost all cases, the common trait is the same: an enormous reservoir of rotational and magnetic energy that is released in a compact environment. All of this leads us to another key aspect of the story. If a magnetar can sustain, fuel, or shape enormous explosions in its surroundings, it can also influence the chemistry of the gas around it. Such a central engine doesn't just illuminate, it can also help create and spread heavy elements. And here, we enter a domain where the connection to us is much more direct: the origin of the materials from which we are made. The violent factory of heavy elements When we think of the elements around us, we often imagine a gentle process, stars burning, forging new nuclei, quietly scattering them when they die. That image is true, but incomplete. To create the heavier elements, those beyond iron on the periodic table, the universe turns to another type of factory, shorter, more violent. In several of these scenarios, a magnetar can be the silent engine that decides how much rare material will be available for future generations of stars and planets. Up to iron, nuclear fusion in the core of a massive star is a profitable process. Combining lighter nuclei releases energy. This energy sustains the star against gravity. But beyond iron, the math changes. Fusing heavier elements consumes more energy than it provides. That's why a massive star collapses when its core fills with iron. However, the universe is full of elements heavier than iron: gold, platinum, uranium, rare earths. These nuclei don't come from ordinary fusion. They need environments where there are many free neutrons and enormous energies. This is where the so-called R process, or rapid neutron capture, comes into play. For decades, the main candidate for this process was a type of supernova. The idea was simple. During the core collapse and subsequent explosion, so many neutrons and so much energy are released that part of the ejected material can capture neutrons and rapidly ascend the periodic table. Later, when it undergoes radioactive decay, these newly formed nuclei stabilize as heavy elements. But it was later discovered that this explanation alone wasn't enough. Another scenario was needed. Neutron-star mergers then entered the picture. When two neutron stars orbit each other and eventually merge, they eject jets of matter that are extremely rich in neutrons. Recent observations of these events, known as kilonovae, show clear signs of heavy element formation. This is strong evidence that mergers contribute a significant part of the cosmic inventory of gold and its companions. But even so, global calculations leave gaps. In some environments, there seems to be more heavy elements than the mergers can explain. This is where the magnetar figure reappears. A young magnetar is surrounded by the remnants of the supernova that gave birth to it. It is not a naked object, it is submerged in an expanding cloud of hot material rich in neutrons, protons, and light nuclei. This cloud is sensitive to any additional energy source at its core. If the remnant were a normal neutron star, it would only contribute its initial heat. But if it is a magnetar with an intense field and a rotation period of milliseconds or even hundredths of a second, the story changes. As the magnetar slows its spin, it injects energy into the ejected shell. It does this in two ways. On the one hand, through its magnetized wind, a flow of relativistic particles dragged by the field. On the other hand, through waves and reconnections of the field itself, which continuously deposit energy. This extra energy can keep part of the material at high temperatures for longer and favor the presence of free neutrons. In such an environment, the R process has more time to act. This means that even heavier nuclei can be synthesized and in greater quantities. Additionally, the magnetar can channel part of the ejection in preferential directions. Instead of a smooth, spherical cloud, regions form where the density and temperature allow for different nucleosynthesis pathways. In some models, the combination of rapid rotation and a strong field produces collimated jets, similar to those seen in certain gamma-ray bursts. These jets drag neutron-rich material outward, where the neutron capture and decay process continues. The result is a pattern of heavy elements that depends on the geometry of the field and the rotation history of the magnetar. Not all magnetars will contribute in the same way. Those born with somewhat weaker fields or with slower spin periods will have less rotational energy to release. Their capacity to alter nucleosynthesis in the surrounding shell will be smaller. In contrast, there is a range of parameters where the effect can be dramatic. A magnetar with a field of around 10 to the power of 15 Gauss and an initial period of a few milliseconds has an enormous reserve of energy comparable to that of the supernova itself. If that energy is gradually deposited, it can inflate, heat, and enrich the ejected material for days. The same scenarios reappear when we think about neutron star mergers. In some collisions, the resulting object does not immediately collapse into a black hole. For seconds or minutes, a hypermassive core can remain, behaving like an extreme magnetar. While it exists, this core expels matter, generates winds, and launches jets. All this activity occurs in an environment already charged with neutrons from the fusion itself. The presence of a central magnetar can increase the volume of material suitable for the R process and alter the pattern of elements produced. From the perspective of cosmic chemistry, this has an important implication. Not all places in the universe generate heavy elements in the same proportion or in the same way. Some galaxies, or even some regions within a single galaxy, may have experienced more episodes where young magnetars acted as central engines for neutron-rich ejecta. This would result in subtle differences in the abundance of certain elements. When we measure the composition of old stars in the galactic halo and observe strange patterns of heavy elements, one of the explanations on the table is precisely this. Perhaps they formed in clouds enriched by one or a few events dominated by magnetars. The connection to us comes in a simple gesture. The gold in a ring, the europium in some electronic components, the uranium in Earth's rocks. All these atoms went through a violent phase. They were part of a plasma where neutrons were captured in a chain onto lighter nuclei. Then they traveled encapsulated in dust grains, mixed in gas clouds, and were incorporated into new generations of stars and planets. In one of those episodes, a magnetar could have been the energy center that determined how many of those nuclei were produced and in what combinations. This doesn't mean that magnetars are the only factory. The landscape is more diverse. There are clear contributions from mergers without stable remnants, from direct collapses, and perhaps from other extreme transients that are still poorly understood. But incorporating magnetars into the list of protagonists gives coherence to several scattered data points. It helps explain why in some old stars we see heavy element abundances that don't fit well with a single type of event. It suggests that the universe has experimented with several recipes to cook up its inventory of heavy nuclei, and magnetars are part of that recipe. It also reminds us of something about the scale of these energies. The work a civilization would perform by burning fuels over millions of years can be dwarfed by a few seconds of activity around a young magnetar. This disproportion isn't just a striking fact. It's a clue as to why the universe can produce complex things from brief episodes. When the energy flow is so high, Nuclear processes that would be impossible in other environments are compressed into moments. Deep down, the role of magnetars in the chemistry of the cosmos reinforces the idea that these stellar corpses are not just theoretical curiosities. They have direct consequences for the matter from which planets, rocks, and living beings are made. Their activity leaves traces in stellar spectra, in the composition of meteorites, and in the properties of distant galaxies. Like it or not, part of the story of our own matter passes through those environments where a colossal magnetic field for a brief time reorganized nuclei and neutrons. The indescribable core. Inside a magnetar, there is no light. There is no solid crust, no polarized vacuum, no visible explosions. There is matter compressed beyond human experience. We know that several times the mass of the Sun fits into a sphere of just 20 kilometers. We know that the density exceeds that of an atomic nucleus. The rest, for now, is made up of models, hypotheses, and limits. The simplest image talks about layers. In the outer crust, tightly packed nuclei and electrons. Deeper inside, a region where the nuclei deform and form nuclear pasta structures. Even deeper, a sea of almost pure neutrons, with a fraction of protons and electrons maintaining electrical neutrality. In that sea, quantum physics dictates that the neutrons can become superfluid and the protons superconducting. That is, flows that move without friction, currents that circulate without resistance. In a magnetar, the magnetic field permeates all of this. Not just the surface, it penetrates the interior and alters the very structure of the matter. The pressure is no longer equal in all directions. The field favors some movements and hinders others. The superconducting currents can trap field lines in thin tubes. The rotation of the superfluid creates small vortices that store angular momentum. When these vortices reorganize, the star can make small jumps in its rotation. These are the glitches we observe from afar. Beyond this image, bolder scenarios emerge. It is possible that at the center, pressure completely breaks down the structure of the neutrons, that the quarks that form them become deconfined and mix into a new, dense and charged fluid. This is called quark matter. More exotic states have also been proposed, such as strange matter, where strange type quarks join the mix and could stabilize a different, more compact core. There is no consensus. These ideas are supported by calculations and analogies with particle physics, but still lack direct proof. Magnetars, with their extreme combination of density and field, are a good place to look for clues. The way they cool over time tells us something about which particles can carry heat outward. The way they slow down as they spin and how they respond to starquakes tells us how rigid their inner layers are and how the superfluid and crust couple. In the future, gravitational wave signals from deformed neutron stars or from collisions may provide more information. Each new measurement narrows down the space of possibilities. There is one limit to remember. We will never see the interior of a magnetar directly. There will never be a photo of the core. What we will have are increasingly refined models, adjusted to a growing set of data, precisely measured masses, estimated radii, cooling histories, activity patterns, perhaps vibrations recorded as gravitational waves. From that, we will rule out equations of state that don't fit and retain the ones that do. In the meantime, these objects have a dual role. They are natural laboratories of ultra-dense matter and also remind us of our boundaries. They show us how far our theories reach today. Beyond that frontier lies physics that we sense but still cannot clearly write down. That a stellar corpse, silent and small, forces us to rethink our ideas about space, vacuum, and matter is not a paradox. It is precisely the signal that in the real universe the rules are not simple, and that sometimes objects that are not black holes can still take us to the edge of what we are capable of understanding.